Come with us now on a journey through time and space to the world of the
Poisson distribution. The Poisson distribution is a discrete probability distribution which models the number of events happening in a fixed period of time or space if these events occur with a known average rate, independently of each other, singly in time and space, and at a constant rate. Okay, so what does all that mean? Discrete means the number of events must be a whole positive number. You can ask what is the chance of getting 3 phone calls in the next hour. You can't ask what is the chance of getting 2.5 phone calls in the next hour. The fixed time period means we're interested in the number of events happening in a certain period of time or a fixed amount of space. We can't ask the question, what is the chance of getting at least 3 phone calls? We have to say, what is the chance of getting at least 3 phone calls in the next half hour? In order to answer questions about the events, we need to know the average number of events per fixed amount of time or space. We call this value lambda, and we write that x, which is the number of events per fixed amount of time or space, is modelled by the Poisson distribution with an average rate of lambda. There are 3 conditions which a set of events must satisfy in order to be effectively modelled by a Poisson distribution. Independence. An event occurring does not make another event occurring any more or less likely. Singly in time and space. Events must happen individually. 2 events cannot happen at the same time or in the same space. And finally, the constant rate. The average number of events in a fixed time or space must be proportional to the amount of time or space being considered. For example, if 3 things happen every hour, then 6 things happen every 2 hours. There are 2 questions we could ask about our events. One of them is about a specific number of events happening. For example, if x is distributed by the Poisson distribution with an average rate of events lambda per specific amount of time or space, and I'm interested in what is the probability of, in that amount of time or space, getting exactly little x events occurring. Now for this, you can just stick your x and your lambda into the following formula, which is in the formula book. E to the minus lambda, lambda to the x, over x factorial. I'll make another video where I talk more about that, but if you're not interested, don't worry, you can just stick everything in the formula. The other question we could ask is about cumulative probabilities. What is the chance of at least or at most a certain number of events happening? And for this, we have tables, but only for specific values of lambda and specific values of x. So for example, if x is distributed by the Poisson distribution with average rate lambda, and I want to know what is the chance that x is less than or equal to a specific value of x, then I look at the tables and I see that I need my lambda to be 0.5, 1, 1.5, 2, 2.5, 3, 3.5, 4, one of these, or if you have a look further down on the table you'll see there's some more here. So anything with a value of a whole number or something 0.5 between 0.5 and 10 is on the table. So we need lambda to be 0.5, 1, 1.5, 2, up to 10. And we need x to be 0, 1, 2, 3, 4, all the way down to, I think this goes down to 20 or 21. So we need x equal to 1, 2, 0, 1, 2, all the way up to, I think it's 21. So for example, if we want to know the probability, if x is distributed with the Poisson distribution with an average rate of 2, and we want to know what's the chance that there will be 6 or less events occurring, then we look down to 6 and we see that the probability of 6 or less events occurring with the lambda average rate 2 per piece of time or space is 0.9955. You need to know the mean and variance of a Poisson distribution. The mean is obvious. We already know that the average number of events per piece of time or space is lambda. That's the rate at which things are happening. And it's really easy to remember what the variance is, because the variance of a Poisson distribution is also lambda. I've done a video proving this, so if you're interested, go watch that. If not, just remember it. If you feel confident you can already have a go at this, then pause the video and try to answer these questions and then zoom forward and check your answers. If not, watch through this example. We're looking at the number of calls in a weekday morning, and x is distributed with a Poisson distribution 2.5. That means the average number of calls on a weekday morning is 2.5, and first of all we're looking for the probability of getting exactly 1 call on a weekday morning. This is a specific value. X is 1, so I'm going to use the formula e to the minus lambda to the x over x factorial. I'm just going to stick all that in the calculator. And I get 0.2052, etc. Now this looks harder, the next question, because we're asked what is the chance of getting more than 2 calls. But more than 2 calls could be, well, you could have 3, or you could have, or is plus, or you could have 4, or you could have 5, or you could have 6, or you could have 7, or you could have a billion, or you could have like a trillion, billion, x equals that should say, billion, there, or one more than that. It just goes on forever. So this is not practical to calculate all of those and add them up because there's infinitely many possibilities. So what we're going to do is we're going to not do that at all, and we're going to actually do the opposite, and we're going to ask what is the opposite of more than 2. Well, that is the probability that it is less than or equal to 2. So the opposite of more than 2 is less than or equal to 2, and then we'll do 1 minus, because all probabilities add up to 1, to get the probability that it's bigger than 2. So 2 ways of doing this, one with cumulative, one is the table, but the table, if you remember what our conditions on lambda are, we need lambda to be 0.5 or 1 or 1.5 or whatever, and we've got 2, oh no, we've got 2.5, that's good, 2.5 we can use the table. Okay, so here's lambda is 2.5, and our x is 2 here, so we go to lambda is 2.5, we go to x is 2, and we look across, and this is a bit too small, I can't see, let's make it a bit bigger, and right, so what we're doing, x is 2, lambda is 2.5, and we get 0.5438, 0.5438. Which is 0.4562. Okay, same idea with this next one. I can use the tables because lambda is 2.5 and my x is 3. So looking at the table, looking across to lambda is 2.5, looking down to x is 3, I get that the probability that x is less than or equal to 3 is 0.7576. Okay, for this last one, I'm looking at the probability that x is between 3 and 5, and it could be 3, or it could be 4, or it could be 5. Well, I could do these individually, to be honest. I could individually calculate the chance that it's 3, e to the minus 2.5, 2.5 to the 3 over 3 factorial, plus e to the minus 2.5, 2.5 to the 4, 2.5 to the 4 over 4 factorial, plus e to the minus 2.5, 2.5 to the 5 over 5 factorial. I could do that, or I could be a bit more clever and use the tables. The chance that it's 3 or 4 or 5, we could think of the chance that it's less than or equal to 5, so that's 1, 2, 3, 4, 5, minus the chance that it's less than or equal to 2. So that's 0, 1, 2, 3, 4, 5, minus 0, 1, 2, leaving us just with the 3, 4, 5, which is what we wanted. And then I can get those two figures off the table. So, chance that it's less than or equal to 5 is lambda's 2.5, and we're looking down to 5, 0.9580. Chance it's less than or equal to 2, 0.5438. So altogether, 0.4142. Here's one for you to have a go at, see if you've got the idea. Pause the video, have a go, and then I'll put the answers up. Pause the video and have a look through these answers and check you understand how they're done. In this exercise, you're trying to use the tables backwards. So pause the video, see if you can get the answer for what A, B, C and D are, and then unpause for the answers. Here are the answers. I wonder if you got caught out on those last two. If you did, look through the method that I've written down and make sure it makes sense to you why the answers are 5. In order to answer this question, you've got to remember what the mean and the standard deviation of a Poisson distribution with average rate lambda are. See if you can remember or look back in your notes, and that should allow you to be able to answer this question. Did you remember? The mean and the variance of a Poisson distribution are both equal to lambda, which in this case is 9. That allows us to answer the problems and get the following answers. How did you get on? Hopefully you found them quite easy. So, quick summary of the Poisson distribution. It's a discrete probability distribution, which means the number of events must be a whole positive number. It models the number of events happening in a fixed period of time or space, and the events must occur at a known average rate, which is known as lambda, per certain amount of time or space. There are 3 conditions which you have to learn for a Poisson distribution to be suitable. The events must be independent, meaning that one event occurring does not make another event occurring any more or less likely. They must occur singly in time or space. They can't happen at the same time or in the same space, and they must occur at a constant rate, which allows you to change the interval of time or space that you're looking at. If you know how many happen in 1 minute, you can double it to find out how many happen in 2 minutes. You can use a formula to find a specific probability of something, a certain number of events are happening in that given time or space, which is e to the minus lambda to the x over x factorial and is in the formula book. Or for cumulative probabilities, you can use the table, provided both lambda and x are in the table. You also need to remember that the mean of a Poisson distribution is lambda, and the variance of a Poisson distribution is also lambda.